Hi, my name is Rick Friedrich from Renaissance Charge and Truth and Heart Ministries, and welcome back to third video. This is just a real short video that I want to add a few more things to the last video. Again, this is in the series of selfish circuits and loving paths as a series now, I guess what we're going to call it. I just wrote somebody on my latest video that I did that really what we want to do is reveal all the free energy technology in simplest form to the common man, and try and remove as much of the technical side of things, demystify a lot of processes and claims, and make them simple and usable. So we want to look at DC, AC, 0-point energy, the whole works. We want to run every type of load that we need, from mechanical load to creating heat, to creating light, to powering pumps, refrigeration, everything that's needed. So we're going to go over step by step just the basics, and we can get technical later on as to the details of the measurements, especially when we get to the 0-point area. That's a lot more involved, and creating unlimited power rather than just doubling or tripling the output. Today I want to talk about the exact same thing that we talked about in yesterday's video. But with solar instead of a battery, because people have solar panels, you might as well use them. But now we can look at still charging a battery with the solar system, and now we're putting the motor or a load in between, again, the two positives, and we're still doing the same thing. Now I have a solar system, or solar panels that I've had for years. I've never used them, never needed them, and but I could show that later on running the system. I'm just going to assume these are the solar panels, and in this case you have to be aware that if we're going to use a 12-volt battery system is actually the solar panels are not 12 volts, of course. They have to be a higher potential, so they're around 22 volts depending on the manufacturer. And so here what we want is actually 24 volts over 12 volts. So 24 volt solar panel system is going to be anywhere from 32 volts to 44 volts open voltage. That means unloaded. When you check a voltmeter across the solar panels, not hooked up to anything, they're going to read these higher voltages. As soon as you apply a load to them, the voltage will drop, is what we were showing here yesterday. The voltage under load on the batteries drop, and the same thing with these batteries, where the primary source under load they dropped, and now they've come back up. I haven't touched these batteries since the video, and this is a day later, minus 6 hours or so. So again, what we want to do is have a double potential under load, which would give us around 24 volts, and this one being 12 volts discharged. We got to discharge this battery once in a while. So then, of course, we are charging this battery at the same time that we're charging this battery. And so this battery you could use, I have an inverter on here, you could run an inverter, or you could just keep this charged up for rainy days, and then run it directly when you need to, and then you could have multiple battery banks here and then go back and forth, whatever you want to do. So I've got a few more notes here. The capacitor, again, in this circuit is what transduces the energy from negative energy to a positive energy, and then the SCR circuit allows you to have 1 volt pulse over the battery, and that absorbs the spike, as I said before, the high voltage. A 12 volts input, which is between these two positive terminals, is a 12 volt potential. That will produce 300 volt spikes here, so we want to absorb that. So really we want a cap that is actually 300 volts, which those are only 100 volt caps, so they're kind of bottlenecking the system. And of course when we go up to 24 volt potential, then we're up 2,000 volt spikes approximately. When we go up to 36, 48, we're way up there. Now again, those capacitors, you're not going to buy the really high voltage ones. It's too much money. You want to get a lot of microfarads in here too. So at least maybe a farad. I've got 60,000 microfarads on those caps each. So they're pretty good. So then the other thing I want to show today is a regulator system. So before that, I'm going to bring this up a little bit closer to you so you can see. And then I will notice also the voltages from yesterday. So the battery, finally, its final resting place went up to 11.98. We started at around 11.83, I believe it was. We ran the bulb, 100 watt bulb, so you can see it drops immediately. We ran the bulb, 100 watt bulb, the whole time we ran the motor, and then it came back up over time. So we actually ran more than, a little bit more than the 100 watt bulb, because we're actually losing quite a bit, like I said, in this inverter. And so we have, at least we have quite a bit more power loss. Now the 100 watt bulb is probably not running quite at 100 watts, and the inverter was drawing 10 amps over 12 volts, so we were there 120 watts, while the system was only drawing from the primary battery about 100 watts. And then we were producing about 100 watts worth of light at the same time. And then we were producing these batteries were being charged at a rate of 100 watts again. So we can see we were in the 1220s, and we have charged these batteries. They're resting now at that voltage. This battery was around 12.4, 12.5, has come down expectedly, and this has charged up. So this is in an equilibrium with the motor system. If we run a regular unpulsed load, this will discharge faster, and this won't be as efficient system as we have with the motor, because some of the energy goes back into this side of the circuit as well as this side of the circuit. You have to understand that. So anyway, these are all the voltages, and what I want to show you today is just a simple regulator system, and we'll look at the schematic again here. So across um, a the trigger of the system, which turns it on and off and regulates the power, we can put a little regulator, and I have it monitoring this battery here. Now I'm not hooked up that way, we'll show that later on, but I want to give you the idea that what we do here is if we're going to run off of this battery, then we want to know the voltage of this battery under load. We can get a sophisticated regulator, which we'll do with our solar charger coming up, but what we want to do is look at, as the battery voltage drops, and we want to turn this regulator, have this regulator turn the motor on. Now if it drops a lot more, we'll turn this motor up to higher power until this battery is charged. Then what will happen is, once the battery comes to a certain voltage, we'll have it turned off. And so then, if you're not using the battery, you don't need to overcharge it. And also, this will then stop charging this battery at the same time. So, we could shuffle things around and charge up other battery banks, run other loads, whatever we want to do. This is just the basic idea. So, here's two real affordable, cheap China products that work infallibly now. So what I'm going to do is, I'm not going to hook them up to the battery here, but just we'll show you the idea here. So you can hear it as soon as I connect this, a relay triggers. So what we have here is two different contacts. Well, one contact goes on and off. So this is just regulating one particular single pull, single throw switch, which then could actually turn the motor on. Now this motor isn't self-starting. Our bigger industrial motor is. This one has only a 40% on time, and we have to actually move it, get it started. The other model of this one, all we have to do is just slightly move it into position, and then it self-starts. So we could, change that to make it self-start with the other circuit. But what I want to show right now is just this. So this is actually just a temperature sensor, which we use in our heating circuits to turn on a heater. And so what it is there's two different voltages. There's a start voltage and a disconnect voltage. Temperature. So you can see if I was to go up there and I don't have the temperature on my fingers, that can bring it up to 38 or 41. But in this case, this is temperature. But we want to do the same thing with voltage, which this one right here has like 5 or 6 different settings, and it takes a little bit to read the Chinese to figure it out. But I have this one set right now for a timer that switches 2 battery banks. You can see the switching there that you're capable with this circuit. So you have 2 different switches that operate where they can come on at different times, they can be related to each other, so forth. And this would give you the capability of, in this case, what I have it set for is to actually rotate 2 battery banks every hour, and that was with this whole mechanism right here. So this is a latching contactor, which gives 4 poles the ability to switch around. And so I actually was using this to rotate 2 battery banks from charge to load. And so what this did is, now you can see 1 minute has passed. What this does is it changes, well actually, yeah, oh actually that's not set to 1 hour. It's but you can make this switch every second, every minute, every hour, whatever timing you want. So that's one way to switch things automatically, or we can set a voltage sense here like I was talking about, and when this battery drops to a certain voltage, this triggers on, bing, and it turns on. For example, what we want to do now is show this idea. So this bulb prevents me from using this rheostat as much as I could to control it. So I'm going to disconnect that, and now we're going to see if we wanted to, we can use multiple settings here to adjust this motor to charge this faster or slower, and so not just turn it on, but how fast. So say this was, you know, running a 5,000 watt load if it was a bigger battery bank, and it was just a lot of power, so we would want to turn this on full blast. The voltage drop on the battery would go real low, and so that would trigger one switch, boom, to come on. Whereas, or you can do this in programming, but this is just a very basic, simple thing that anybody can do. Or if it was just gently discharging the battery, maybe we want to only run this in the lightest mode. So we're gonna run this motor now with a 300 ohm rheostat, and adjust the motor so that it comes on at we can adjust it to different levels. So I want to show you the voltages and so forth in this. So I'm going to turn it on, listen for the beep, ding, and that means it's all good. If you don't hear that sound when you hook it up with this trigger coil system, then something is wrong. Something is maybe blown out or not connected right. So you should hear that, at least with the bigger motors at least. So we're going to get this started, and I'll have to probably adjust this a little bit and just look at some of the voltages as I change things around. So now it's really high, so I'm going to adjust it more so it gets started. So you can see, so let me spin it a little bit faster to get started. So this is at a real low level. Now, so this is just getting it started here. Now with the other MOSFET circuit, or the other triggering, which we have in these wires right here, there's an opto switch inside that we can use instead of the trigger coil. And so let's just get this up to speed a little bit. I'm going to just use this bulb to get it going. So you can see the voltages, whatever they are right now. I'm going to look at the ammeters here. So you can see the voltages are affected by this, and we'll look at the amperage. So we're only at 5 amps around, 5.2 amps. So this is a lower level. Now I can adjust it from this point even lower. So we'll look at these amperages here. So there's 3 amps, And you can see the different voltage levels here. And then what we'll do is we'll come back up with the bulb. Now it's pushing, it was pushing 12, now it's gone back to 10, 11. So it's about 11 amps here. And then I can turn it. So we got it back to around the 10 amps that we were yesterday. Now we can see again the voltages. Now of course this is under charge, so it's going to be higher. This is under load, so it's lower. And this is under charge as well. But this voltage rate is more stable, more of where it's at, because there's only a 1 voltage difference between this and that. So if we looked at that without the capacitor, the voltage would be higher. The voltmeter would recognize more of the pulsing than the stability of the battery. So it's really, you know, this is more an accurate place. Now if I put it under load, you can see the voltage drop. I think I've got something on the screen. Scratched up screen. Anyway, so that represents again a practical system that could be run with a solar system, wind, hydro, waves, whatever input you want to use, grid power. We want to get away from the grid power, of course. But. So let's look at that again. And see, really, it didn't affect really the input side. So let's turn it off. And I think that really covers everything here. We can look at the voltages for a little bit longer so you can get a feel for it. But anyway, I have a bunch of these kinds of products here that I get off of eBay, and you know, you can use those other systems too, that Adreno or whatever they're called, that you can program, or you can get a programmer. What we're going to do, we'll have some of these regulators available soon, so that you can use this system in an automated fashion. And then what we'll do is we'll have actually a complete system eventually. This is complete in itself. It's just a matter of adding more and more features. Like I said, once we add the 0-point process, then all batteries will charge up, and we can add as many processes as we want to the system. Once all that, what we'll try and do is actually make a system, several different size systems available, so none of the calculations or anything has to be worked out, and that it will be safe to use without you blowing up any parts or something like that. But this particular system that we're doing right now here is straightforward. It's pretty simple. The common man with some basic electrical understanding, not prejudiced against this kind of technology, can actually utilize, again, with the right arrangements of the batteries, of the potentials, and understanding the negative energy side and the positive energy side. This is all you really need to understand. You don't need to get all these complicated things figured out. Once you have this basic idea, then you can have all the power you want. At this point, like I said, we're working with batteries, and you know, we will develop AC systems and batteryless systems as well. It's not as easy to do that.
Hey, buddy.
I'm just showing these voltages.
Are you going to be around tomorrow? He's coming down here.
If I can convince him to stop in, I'll call you. Whatever it says, I'll call you.
Yes.
All right, guys.
He's in the area, you're in the area.
Thanks, Mike.
Let's set something up. Thank you. Thank you, Mike. I'm going back.
Hey, he also does LEDs.
Oh, yeah.
We're going to
LEDs.
So the only thing, guys, is we got these two cameras going on this side. And then you guys can stay in the middle so I can get this going on YouTube.
Sorry, Rick. Thank you.
Yeah. So yeah, just guys watch the flow of the cameras here. That's all. But what we have here, I don't mind you coming in and looking at any point either. What we have here is the system right here. Like we talked about, combining these two processes, where we have two battery banks. This part of the circuit, which again is also on this diagram. Battery number one, which is 24 volt. Well, actually, in this case, we're running 48 volts. We're using these smaller batteries here, 35 amp hour batteries at 48 volts. You can see they're 49.56 right now. And then the battery bank here is normally two parallel batteries, but because these are actually 225 amp hour batteries, I'm not going to bother paralleling them up. And we've already seen, you know, that kind of demonstration at the 12 volt level. Now we're going to run this 48 volts in parallel with 24 volts here. You can see it's 25.1. And then we have the charging battery bank, battery number 3, is also 24 volts, 225 amp hours. And I have two inverters on each 12 volt section. We're going to run 300 watt loads on that. And then we have 4 generator coils, like I said, with 4 LEDs, not shown in the diagram. And they're going to run, you know, fairly bright. I don't want to run them at full brightness and blow them out because they don't have the heat sinks on them. I have a little fan here to cool off the MOSFETs and the little radiator there. Now, what I have here that's different than what we just showed, on this circuit, we have the capacitor, which is these probably 60,000 microfarads. They are 60,000 microfarads, 100 volts. And what we have there is across the output, what we call the output, and we have an inverter then across the batteries. Now we have an SCR circuit here, which is triggered by a diode only, to pulse across the negative of the capacitor and the battery. This creates about a 1 volt difference, so that what's happening is we don't want a high voltage spike to either be suppressed by our inverters, or damage our inverters. So we have the capacitor sort of, you can look at it as a buffer.
Directionally discharging.
Yeah, but it also converts this energy, what we call this negative energy here, we're converting it, the capacitor converts it to a positive energy. So we can positively charge this battery then, and then you could actually measure current flow between the capacitor and the battery, and so forth. So,
As long as you don't short the caps out.
yeah,
When it was on the tabletop, where was the capacitor?
there was no
involved?
capacitor. It was just going straight to the battery bank,
Yeah, okay.
and then we had the inverter across it.
So you're using the caps to buffer any spikes.
Yeah, but also to convert the energy from a negative to a positive type of energy, which
Okay.
if you were going to rotate these batteries around, you'd have to
Negative
do
to
that.
positive direction.
No,
Neg-
no, the battery actually in its atomic level becomes negatively charged, which, like I talked about with one of you just a minute ago, if you were to charge the battery up with a negative charge over time, all the positive charging that you normally do in a regular battery charging system
Go away.
would be gone, and it would be actually fundamentally different battery. It takes a number of cycles to do that, maybe 10 cycles, maybe about a month. After you've done that, if you actually attempt to charge the battery up with a regular, like discharge it and charge it up with a regular battery charger, it won't actually take the charge until it converts it back to a positively charged battery. It has its benefits, it has its drawbacks, but this is one interesting factor when you know you have a real system like this, is when that takes place. And some people think that their battery has been ruined when actually it's become negatively charged. And it can still function like a regular battery, except now,
Does it change poles?
no, it doesn't change poles, but at the atomic level, it's actually
Negatively charged?
changed. Yeah, I mean, I'm not going to get into all that
Okay.
detail right now, because I'm not the one to explain that. But anyway, we're going to run this big fan here as some of the mechanical load. The rest of the mechanical load is on the generator coils. And like I said, I have the speed control, so right now it's pulsing slower, and then I can adjust the speed. As long as my temperature is good to go, then we'll put it up to full. And then we'll look at the amps right here. I got an amp meter set for 100 amp, and it shouldn't go above somewhere between 40 and 60 amps because I'm running off these batteries. So I'm just going to put it in position, and then it will start. Oh. So you can see it's pulsing slow. So now what I'm going to do is turn it up. It's growing. So you can see, of course, the input battery is discharging under this load, which is, right now it's 26 amps. So I don't have it at full. And this charging battery, you can see it going up in real actual power. I'm sorry, this is the charge, well, both of these are charging batteries. Of course, this one is the parallel battery bank number 2. So the energy is supposedly being transferred. So now we're up to, 24 amps only. So we're not running it very hard. We just want to make sure everything's cool here. We're at 83 degrees, which is fine. This is going to get warmer, of course. So ideally on a bigger system, higher voltage, we're creating more heat here. We could actually create a heater in a facility of some sort. So, these batteries are limited. I really should have brought the other bigger batteries in here, but I figured it would be easy enough to set it up like this. But yeah, so we've got 26 or 23 amps at 24 volts. Well, you got to just figure out the voltage difference between each bank here is the operating voltage. So you just have to run, just calculate 26, so 20 volts right now. We're running at 20 volts And we can run that for a bit. I'm just going to get my camera out here so I can show this close up.
So this other bank of 4 coming off the caps is like on a trickle charge now? So
it's only 22 amps, whatever. Yeah, so this one position and then it will start. Oh. See, you can see it's pulsing slow. So now what I'm going to do is turn it up. Oops, wrong way. So you can see, of course, the input battery is discharging under this load, which is, right now it's 26 amps, because I don't have it at full. And this charging battery, you can see it going up in real actual power. I'm sorry, this is the charging, well, both of these are charging batteries.
coming off the caps is like on a trickle charge now?
Hold on. So it's only 22 amps, whatever. Yeah, so this one, which one are you referring to? So these batteries, oh yeah, so what we want to do is, these ones are being charged up, and we're going to run, we can run a load off of them. I was going to run this a little bit faster, and we can run this inverters. Of course, it's going to go down a good bit here under load, but I just want to show the basic idea. So now you can see under a real load, the batteries are going down, of course, under that load, but it's under operating load, so it's going to be different than resting load, of course. So yeah, if we didn't have the caps in there, you would see the pulsing and bring up the battery voltage, because under charge, under a pulsing charge, the meter is going to show a higher voltage. Like once we stop this, you'll see the batteries level out more back to where they were. Which one are you referring to?
These 4 coming off the
So these
caps.
batteries, oh yeah, so what we want to do is, these ones are being charged up, and we're going to run, we can run a load off of them. I was going to run this a little bit faster, but those batteries can only put out so much. But yeah, these are being charged. Well, see, the difference is,
They haven't changed nearly as much as the other.
yeah, because it's representing more of the state of charge, whereas that one, once we turn it off, you'll see that they'll more level out, whereas this one will stay more stable. In other words, this one's representing its actual real state, because we only have 1 volt difference over this. So if I didn't have that capacitor, yeah, you would see it being much higher, right? So that's the difference is,
But it's still charging.
yeah, it's still charging.
Positive coming out of the caps.
Yeah, so then we can run this inverter. Of course, it's going to go down a good bit here under load, but I just want to show the basic idea. So now you can see under a real load, the batteries are going down, of course, under that load, but it's under operating load, so it's going to be different than resting load, of course. So yeah, if we didn't have the caps in there, you would see the pulsing and bring up the battery voltage, because under charge, under a pulsing charge, the meter is going to show a higher voltage. Like once we stop this, you'll see the batteries level out more back to where they were, more or less. So really, I've got a little bit too much of a load here for what we're pushing. But that's all right. So and you can see, of course, these are only 35 amp hour batteries, and these are 225 amp hour batteries. You know, there's a big difference there in capacity. And that's why these are, you know, obviously pretty low under this. I think under the circumstance one of these batteries maybe a little bit lower than that. So anyway, we can take off the fan right now and let it spin a little faster. You can see the LEDs light up a little bit. So right now we can see the voltages.
So it spiked back up a little bit, not much.
Yeah, I need to actually push it a little bit harder for higher amps with bigger batteries to get that running a little bit better than I did here. So now we're going to run this, and it's going to go a lot faster, of course. Just don't stand in the direction of the magnets, you never know when they fly out. So now it's operating at a different level here. So you're going to see more of a little different of the charging. And we're at only 13 amps right here. You know, not under that load. You know, of course, you got to just balance out all those things. But you can see, you know, the charging rates and all that. Here, you're going to see more, a little different of the charging. And we're at only 13 amps right here. You know, not under that load. You know, of course, you got to just balance out all those things. But you can see, you know, the charging rates and all that. We can look at the voltage of the capacitor in comparison, just so you can get an idea here. So across the cap, we have 2411. So it's about 1 volt difference between
The battery and the
yeah. And so, well, the other thing I didn't mention, when we look at, I mentioned it to one of you just now, I want to mention it here again. When we look at the basic circuit, right, notice that the batteries are not in parallel to each other. They're in series. If this was in parallel, you would think, okay, the energy from this battery is transferring into this battery. But actually, they're in series with each other. So from, see, they're in series across here. So from here to here is 24 volts on a 12 volt system. So you'll notice this, on the negative side, is actually connecting up to the positive. Well, on this diagram here, so this negative terminal is actually connected to the positive. So that you got to realize that this energy here is contained on this side of the circuit, and it is not charging this battery. Something else is charging this battery, which is what we call energy from the vacuum. So anyway, you can, I'm not showing this as a means of trying to prove something to any of you right now in this short period of time, because you have to ultimately see voltages over time. You got to know the condition of your batteries. You know, usually starting off with brand new batteries out of the factory, you don't have to worry about reconditioning them. They're good to go. And then you can do your own controlled test. What I'm trying to show you here right now is just a demonstration of how it works, how to set it up, and there's nothing hidden here to know about. There's no little secret trick like a lot of these inventors. They'll do a demonstration and then there's something missing from, and you never quite figure it out. And it's not about doing that. Right? What I've always been for is helping people make these things work. And so like I said, this represents the intermediate level of running things. Whereas, you know, this system right here, is the basic level. You know, when we had this set up over here with just the 2 batteries, that's the basic level to get people to understand there's 2 different types of energies here. The battery's charging on its own somehow, and then now we're showing here another additive process with the batteries in a parallel configuration here, in which there's another whole element here. So like I said, we turn it off, and let's see the temperatures here.
Make sure. Yeah, so we're at just under 100. We're good to go.
And again, like I said, we could create free heat here on the circuitry, and then we could actually do that in the coils and do that. So let's turn off the inverters, and you can see this battery bank will charge up over time at the rate that this is discharging.
Do your motors and generators, motor coils and generator coils also create heat?
Yeah, the motor coils in this particular configuration can create heat.
That's what you were talking about, having the hollow cores and the water cooling.
Yeah, we could do the water cooling in that situation. We can, you know, like I said, the circuitry itself.
As soon as you took the load off, this one spiked up.
Well, yeah, and then it's going to spike up. You know, so that was 600 watt load there. And then, of course, we had the load. Well, that was the electrical load in that sense. And we had mechanical load from the LEDs.
Oh, yeah.
And the fan. So, I mean, it's actually not as good a demonstration as I wanted to do, but I just kind of brought this in at the last minute. I was going to show another motor with the trigger coil, and then I added that extra process that blew the whole thing out. I had too much power. I was going to show that, but then I damaged the circuitry at the last minute, so I brought this one instead. But it gives you an idea, 12 volts, 24 volts, and we can run this a lot harder than what we're running it right now. This is just running at the basic mode and basic power level. But we can run this probably, I could probably get about 5,000 watt output on this system with inverters, and that when we run it at the higher voltage and higher amperage input. Of course, these batteries, we're not going to be able to sustain that. And they're going to come back to roughly where they were. And then, of course, this battery will have received some charge.
So to get to 5,000 watts, what voltage were you, how many batteries?
Well, we're going to be looking at a 48 volt system. See, the limitation of this particular motor is that we have cores in there, and we can only run without cooling them to about 15 amps per coil. So 15 amps times whatever voltage you want to run is the limitation of that motor in power level. And then of course, if we have some air cooling, you could probably push it up to 20. You know, as long as those cores in the center won't get too hot. You can do air cores; they're not quite the same power level, mechanical power level, but you could do the charging level with the air cores. Nice meeting you.
As the water cooled.
Yeah, then you can do the water cooled. Now, the only thing is, with this size of a motor, we can't wrap the copper tubing around.
This small spindle.
Yeah,
You have to size your spindles
spindle
to get
is
them,
too small.
keep them cracking.
So yeah, we make a bigger model or just bigger coils.
Sure.
Then yeah, we can do that like we're going to do with the model Steve's going to have is
Bigger coils,
we did that
bigger
with
tubes.
bigger coils in there. We can run high
some
amperage
water
through that, high voltage.
It draws amperage, doesn't it?
Okay, you mentioned heat.
Well, we went
You
to
can
300
heat. You got up
amps.
to 100 degrees of cooling.
What's that?
Run it through a cooling system.
Yeah, we can run it through a cooling system.
Have you
or-
done that
Yeah, we've done
to,
that.
to raise efficiency?
Yeah, definitely.
Easy to put a larger reservoir on there.
Yeah, I mean this is just represent a very small system
Yeah.
for showing.
Have you done that though? Have you cooled the liquid going through the?
Yeah, we've done that on the bigger. On the bigger system. So yeah, so that way we can run, you know, like literally hot water heating in your home and stuff like that.
Yeah. Maybe that's, yeah. Put it in, I can put this in place.
That's kind of what I was thinking.
And you can run through your hot water
Building
system.
out back or something.
Yeah.
So
So these are slowly climbing back up this bank.
yeah, because it was under load, you know, and of course, what I should have done is actually not have the loads on first and let you see the battery charge. And then well, I did for a little bit. We did for a little bit.
Yeah.
But it was what I'm trying to say is when a battery is being charged with the pulsing normally without the capacitor, it's showing you not the real state of charge. It's showing you a higher voltage. Just like these ones, like this one's coming back down because it was getting this peak pulse.
Sure.
Whereas this one was going through the capacitor at a 1 volt pulse. So this was actually,
Like a trickle.
yeah, it was representing more of the, before we had the load on it, the actual state of charge. Which is very hard to move these batteries up fast. You know, these are, 225 amp hour batteries. And normally, you know, with a golf cart, what they're used for, you got 30 amps over 5 hours charging before they go from discharge to charge. So we were running only what, 10 or 13 amps on this side, and we were seeing it charge up at a decent rate. Now, this presentation is not attempting to show all the calculations, all the particulars running it. Otherwise we would have equal batteries here and all that. But it was just to show a simple demonstration of how it works, so that people can do the same thing. Now the speed control and all that are not necessary. We can use transistors and the sort that, like I said. It's just the MOSFETs in there make it less components. And
Which can you control better, the transistors or the MOSFET?
so transistors you can control better. And we can get into bigger transistors than that.
Yeah, I mean, we can pick
It's just a matter of sourcing them and getting the right ones. And then you can control, but they do draw more energy, to switch the case of
significant
MOSFETs
amount.
are less energy, and but they are harder to control. So.
What's the significance of the one battery set being half the voltage of the others?
Well, it's creating a different potential between, you've got 48 volts here and 24 volts there, and what some have called splitting the positive here. We're running between the potentials. So for example, this is what I showed on here. The negative end of the motor is going to the positive of the
If they were 24, if it was 12 volts up here, the motor wouldn't run.
Yeah, there'd be no potential difference between them.
He describes it as a waterfall. That's how I get it.
Yeah, so if you look at that,
24 is 24 feet high, and you got 12 feet.
yeah, if you look at the diagram as a waterfall, battery 1 is representing the the higher level.
It's a higher voltage.
Yeah, the higher voltage and the water up higher, and then the motor is representing the wind turbine or the turbine, whatever. The water is not the water is still going into battery 2 or reservoir 2. And normally you think that the motor would be consuming the water or the power in an electrical circuit. You think the motor is, but this is in demonstration to show, like the bulb circuit, that the motor is actually running for free. And so it's going between the two potentials.
And battery free in your waterfall scenario, or
it doesn't relate to that analogy, actually.
Well, but it's connected through here.
Well, it's actually just across the coil, and it is not because the batteries are not in parallel with battery 2 and 3. They're actually normally when we have it just the 2 battery bank system, the batteries are in series connection, as you can here. This is the easier way to understand that circuit. That's why we do this in stages. So the batteries you see are in series with each other, battery through this connection here.
Yeah, that one is easier to understand. This one's more complicated.
That one's more complicated because I have 2 processes in there. You know, all 3 with the capacitor.
It's still curious as to the potential between these 2 plus and this negative and this negative.
Well, you can measure that right now. Here. So we'll go with.
You can do that on the little one here.
So give me another. Well, here's another one.
Yeah, let's do it on the little one because that's this.
Oh yeah, let's do it on this little one.
Put it set up like that.
So. And that's why we want to do the little one first, because it's easier to look at. Not as many parts. So we'll look here.
We have to do it when it's running.
No. Capacitors. I'm going to just bring this camera up here so we can show it close up, because I'm probably going to use this camera.
I called my cousin, who's like a head electrical engineer at a medical device company for the last 30, 35 years, to see if he wanted to come today or could get off work. And he's really interested. He's into that kind of stuff, you know. And his first question was, "Where's the heat going?" You know. So,
yeah.
But like you said, you started out about 80 and went up to 100. So there's a
Oh yeah, I mean,
there's definitely a heat benefit, but it, you know, my concern and his concern were, you know, the overheating and possibly explosions. You know?
Oh yeah, just like any kind of.
When I saw a bank of caps and a bunch of batteries.
Oh yeah, sure. I mean, just like any kind of electronics, you got to deal with all that. You know, and you could have. What we do is we have on the bigger motors, we have thermal protection in there. Sure. It will shut off. We have, you know, fuses and all that.
That's what I was thinking.